So the Grignard reaction. I'm going to try and make this a little simpler and maybe hopefully quicker, but we'll see how that goes. We'll start off with our starting material, bromobenzene, and this is just an example that came straight from the bottle. And so the typical thing is, look at your functional groups. This one is essentially aromatic. The fact that you have a bromine or halogens, whether they're on a phenyl ring or whether they're on an sp3 carbon, they're not normally very diagnostic with IR. So we can basically just look at the aromatic structure, and you can see what's interesting here. The peaks that are that side of 3000 are the carbon sp2 hybridized with a hydrogen stretch. It's kind of interesting is a 2924 and a 2852. So the question is, whoever took this in the bromobenzene bottle, that doesn't make sense that it's coming from the bromobenzene itself. Maybe there's an impurity that's actually in the jar, who knows. The biggest, 1, 2, 3, 4 peaks, if you see those classic 4 peaks, those are the overtones for a monosubstituted aromatic ring. Clearly the 1578 and then these two here, these three in this particular IR, clearly is the carbon-carbon double bond of an aromatic ring stretching. And then the monosubstituted outer plane bending, there's always two. And this has a little bit of two, I don't know if it bifurcated, sometimes they'll call that on the absorption. Maybe it's a little too concentrated, but those two main absorptions right here are definitely the monosubstituted outer plane bending. So that's pretty much good for the bromobenzene out of a jar. This is benzophenone. So again, what you're going to see here is mostly aromatic structure plus a carbonyl. We can start with a carbonyl. Anytime you see that carbonyl, you always look right around 1700. This one's at 1752. Why is it not at 1710? So if you look inside Pavia, clearly when a carbonyl is in resonance with a double bond or a ring, it'll drop it by roughly 30. If you have two of them, it could drop it from 40 to 60. So this one dropped it all the way, a good 60 units, all the way down to 1652. But that is it. Aromatic structure. Now it's funny, and then you see that little spike. That goes along with, in Pavia under aromatic, not aromatic, carbonyls, it's an overtone of your carbonyl absorption. So when you see a relatively nice flat baseline in this area with a little spike like that, that would be the overtone. Notice how in our bromobenzene, how strong and prominent those CH stretches were of the aromatic. But when you look at benzophenone compared to these peaks, look at how small they are. That happens a lot in a lot of compounds. There's no guarantee that the CH stretches of a compound are going to be very, really tall. So these ones just over 3000 are the CH stretch of the sp2 hybridized carbon with a hydrogen stretching. And these are both monosubstituted aromatic rings. So down here, this one's a little more perhaps trickier, but you definitely have to say that these two right here are going to be the monosubstituted out of plane bend. And there is no nice pattern of overtones in this one, at least showing. Rerun it again, and sometimes it does show. The product, triphenylmethanol. So again, this actually was triphenylmethanol that I took right out of the jar, so it's a pure run. This is not someone's sample. So in any event, what do you have here? Aromatic. There is no hydrogens on the carbon that's sp3, but you have an OH. So we can start with the OH, and sure enough, the OH stretch, should there be one, happens this side. So this one here, not a lot of hydrogen bonding going on because that's why it's sharper, but that right there is your OH stretch. The carbon to oxygen alcohol absorption. When you look in Pavia, and this is kind of interesting, this one really shows it nice. If it was primary, right around 1050 it would be. See how that's kind of strong? But because this one is a tertiary, it's supposed to be closer to 1200, or in this case 1150, and it turns out on this one there is no other strong absorption, so that 1157 has to be the CO stretch. Now we go back to the aromatics, so yet again we look down here, the 2969 and that's got to be some kind of impurity of some sort that has sp3 carbons, but these two are definitely your CH stretch of the aromatic carbons and a hydrogen, and somewhere around 1600. So the 1597 is one of them. 1490 and even the 1445, those collection of three have to be carbon double bond to carbon of the aromatic ring stretching. This can't be part of a CH bend, certainly not that prominent for this compound, because there is no hydrogens on the carbon bending. So that's the IRs. Let's move on to the NMRs. So what I did was actually take bromobenzene out of the jar, and I ran these on our instrument. I even put in some TMS, right? So I had a good 0 on that. So here's our bromobenzene. And all you have is aromatic structure. You're not seeing, on a 60 megahertz instrument, you're not seeing nice doublets or triplets or things like that. It's a forest of peaks. The best we can do, though, is look at the integration. So it's a 3:2 ratio. We know there's 5 hydrogens on there. So you can see how there's almost like one little forest of peaks and another one. 3 of the hydrogens are here, 2 are here. There's a little bit of a space. But carefully notice exactly where these 2 humps are occurring. 7.2, 7.4. So that second hump is at 7.3-ish. Move to bromo. Sorry. We might as well look at the carbon first. So bromobenzene, it's monosubstituted. So sure enough, the attachment carbon is the short one. It's quaternary. So that short one has to be the carbon that the bromine is sitting on. Then you see the 2 ortho ones, the 2 meta ones, and you see 1. Now, notice how in this case, all 3 of the other carbons are similar in height. So without knowing and having a reference, I couldn't assign these 3 with this spectrum, but we definitely can assign the 1. And as expected, there's nothing else. So let's just remind ourselves, the bromobenzene had 2 little forest peaks. The one on the left, 7.3-ish. So we take a stroll over to, out of the jar, benzophenone. Same thing, 2 sort of, batches of little forest of peaks. However, notice how it is considerably closer. And how do we confirm that? Because that TMS is added, so this is good. Notice how that second blob is almost, there's 7, 7.5. That's like 7.8, 7.6, that second hump. So definitely, if you were to mix benzophenone and bromobenzene, the NMR would definitely show you a different little blob of peaks, forest of peaks. NMR, the carbon-13 of benzophenone, each of those aromatic rings is the same. So the attachment point on the ring should be a nice short quaternary carbon, and sure enough, you can see it right there. The other quaternary carbon in that molecule is the carbon of the carbonyl. Because it's a ketone, should be past 180. So there it is, just shy of 200, that little peak quaternary. And then, of course, the ortho hydrogens, there's 2 of them. The meta, there's 2 of them. And the one at the bottom, the para position, only has 1. So very often, and it does that this time, this is the para one. It's shorter, clearly half the height of these 2. So these 2 would be the ortho and meta ones. And there's nothing else in there. That's a little bit of TMS. So now we move on to, this is out of the jar. So this is not one of the students' ones, their product. This is right out of the jar. And it comes out super nice. So there's triphenylmethanol. And clear as day, this is kind of funny. See, the integration here is 14.7, which is 15 hydrogens, because there's 3 rings, 5 each. And right at the aromatic, look at that. It's almost like a giant perfect singlet, which is rare, but there it is at 7.2-ish. How do we manage to integrate it? When I took this out of the jar, I managed to get the OH hydrogen to show up. Folks, most students rarely see theirs show up when they run their crude product. It rarely does, but out of the jar, it is variable. If I was to rerun this sample, slightly different concentration of chloroform, that little peak there would be moving and sometimes doesn't show up at all. But for this day, perfect integral of 1 relative to the 15 of the aromatic, so it works out good. But notice how clean and flat that baseline is. These things, you should note this. A lot of signals give what's called spinning sidebands. See how it's like an echo? There's one there and one there, one there and one there. Those are echoes off this big singlet. So you learn to sort of ignore those. So when you increase the volume of the noise on your baseline, you can see those. So you get used to sort of ignoring them. Now, as far as the carbon of this product, and this compound is on SDBS, And it does turn out that in the aromatic region, only a few show up, so some of them are actually almost perfectly overlapping. The attachment carbons is this one closer to 150, the para-position ones is this one, and the other two sort of lump together and form a big singlet. On a higher resolution machine, that big giant peak there would kind of separate into the two others. So you might see that on SDBS. This was run in chloroform, and there's a note right here. Triphenyl methanol from jar. Note, the peak at 82 is the peak from the triphenyl methanol, meaning that one right there. These next three are the classic three from chloroform. So it is hiding right there when you assign the carbon for that. Now, as far as students, just show you real quick here. Here's one student. This is, I don't know what year this was. 2011, Andy and Christina's. So see the product, there's that nice big singlet for them. And when you carefully look for an OH, see that little blip right here in the baseline? Believe it or not, that actually is the OH, but it's not very obvious, not at all. So that's why we don't even bother integrating it. And then you look to the left of that, and clearly you can see the one closer to 8, see the one little blob and then another one there? That's a small amount of benzophenone, and then this one here, bromobenzene. So clearly that shows a very, very small amount. Let's look at the next group. Oh, there's that blip again. This is another student. See that blip near 2.4-ish? That's their OH of their product. See that looks like the remnants of ether, a little triplet, and there was the quartet. Not big enough to integrate. Obviously, this group had a lot more benzophenone and bromobenzene. This one clearly is integral. You can integrate this and put it in relation to your product. Trouble is, some of the integral of your product buried right in here is a little bit of the bromobenzene adding to its integral. That's why, if you could have found the OH peak good, the integral for this peak, which should have been 15, will work out to be a little bit smaller. So you can see what you're looking out for. You can definitely look at your NMR and identify leftover bromobenzene or benzophenone.